So this video is about the thermodynamics of surface tension. So usually the way that surface tension is introduced is that it's the force per unit length. So like if you want to stretch a film of water or something like that, right? So to stretch that, maybe it's between two needles, I don't know. You want to stretch this thing, then to stretch that you actually have to apply some force, and that force upon the length of this region where the water molecules are interacting with this needle, that thing is what we call a surface tension. And you would have seen this other approach of defining surface tension as well, which is the work done by us upon the change in area, so delta A. And taken to a very extreme and precise case, we'll just say dw upon dA, or partial w upon, okay, it doesn't really matter. As long as we know the context, you don't have to put partial derivatives here. So it's the work done by us upon the change in area. That makes sense? Okay. But many times, when we say dw, this is also sometimes written as du, that is the change in energy of this fill upon dA. So this relation dw equal to du, this is not very obvious in fact. So somebody might have wondered, why is it that the work we did is actually equal to the increase in the energy of the system? What about things from external surrounding? Yeah, what about that? What about heat transferred or some other form of work? What about those things? So this video is in fact about proving the fact that the heat transferred is in fact zero. So first of all, we'll start off from entropy. So for liquids, the entropy is basically given by you can actually figure out the entropy by um, considering these molecules, right, in the form of some kind of lattice. I know it's supposed to be liquids, but yeah, we'll just consider them to be in form of a lattice where each point can vibrate a little in this space. Okay, right? And these can in fact shift, right? But then that doesn't actually change the complete appearance, so the change in entropy would just be zero, because it's basically like yeah, you just switch these two and then it's the same system once again, because it's still the same kind of molecules, the same kind of situation, so no change in entropy, right? So you can just assume them to be in kind of a lattice, even though that's not what exactly is happening. But if that's the case, right, so you got this lattice, and these molecules are vibrating, right? So somewhat like a solid basically. And then right, the number of different states that the system can take, right, that is basically what entropy will be. So these molecules can, so if I number these molecules as 1 2 3, I don't know, yeah, just keep on numbering them, right? So 1 2 3 4 5 6 7 and then 21 of these, I'll just number them, and then I'll start to switch these, so basically like rearrange these guys, right? So number of ways that I can actually rearrange these guys is 21 factorial, right, because there are 21 of these, and then 21 positions on the lattice, right, where I can have their mean position. So this is the mean position of this guy, and it can actually vibrate, so it doesn't actually stay in that perfect position, but yeah, almost on that position. 21 factorial, yeah, right, this is the uh, number of ways that you can have different states for this system. And then what we do is do kb, so the Boltzmann constant times natural log of this number, right? So that's what we call as entropy. So for a large number of molecules, say n molecules, this will basically be natural log of n factorial, right? Yeah, and the thing is, each of these lattice points is unique, right? And each of these atoms are also unique. That's what I'm considering. So it doesn't matter what properties these lattice points have, as long as they are unique. That is, you cannot I mean you cannot get confused between two lattice points. It's okay, you can just have n factorial the ways. So now what would happen if some of these lattice points were more energetic and some of them were less energetic? It would still be n factorial, right? This thing would still be n factorial, so the entropy is given by still the same expression. So now we can finally go to the liquid and air interface thing, right? So this top surface, so this top layer of molecules, these are more energetic because, yeah, they don't have those cohesive forces that they had when they were in the bulk, right? Because there are no water molecules over here or whatever liquid you are taking, and air molecules, right, those don't interact much with it, right? And because of that, these states are more energetic, but these states are still distinct from all these states, and then these states are still distinct from every other state, which means that the entropy thing is still given by this, right? Okay, so as long as the number of molecules stay constant, it doesn't matter what shape your system goes in. So maybe we could, change this thing a bit. So maybe like you push these guys inside and try to change the thing a bit. So now you will have these three guys like this. That's our new surface or something. So you got more molecules now, right? But still it's the same entropy. So kb natural log of n factorial. And because the entropy remains constant as long as the volume, basically volume is proportional to the number of moles, number of atoms under constant temperature, right? And constant pressure as well, right? Okay, so because of that, actually maybe I should not say constant pressure, but whatever. The thing is, as long as the number of atoms or molecules or whatever, those remain constant, what we'll have is that the entropy will actually not change. And what that means is, you can just say ds is equal to 0 throughout whatever reversible process you want to do for this system, right? And I'm saying reversible, there's a special reason for that, because when you're doing irreversible processes, in those cases, you cannot actually pause for a second and actually look at the microsystem, right? That's kind of a hard thing to do. Yeah, so reversal processes is what we'll use. And also for irreversible processes, a lot of equations that we'll use don't make sense, right? Yeah, because there's like a lot of other factors, kinetic energy and you know changing interactions and whatnot. So yeah, just deal with reversal processes. So very slow processes, um, with no spontaneity, right? We'll deal with these kind of processes. So for these processes, ds is equal to 0. So the entropy of this whole system is 0, but then because these are reversible, the surrounding entropy, that should also be not changing. So ds surrounding is equal to 0 because ds universe must be 0. So you can just conclude this thing. And from these two, it's pretty obvious that the heat transfer between these two media, right, that must be 0, because this is what we are considering as our system. So there should be no heat transferred to the system because ds equal to 0, and no heat transferred to the surrounding because ds surrounding equal to 0. Now this thing is actually not necessary. Maybe you have something else that's the heat source, right? Then it's not going to be equal to 0, but you get the idea, right? We are not going into those kind of complicated scenarios. We're just taking the surrounding, the air basically, and this liquid. That's it, that's all we are doing. So the thing is ds equal to 0, that's what matters. This may or may not be true, but we don't actually care about that anyway, right? So ds equal to 0. Yeah, and what that means is that dq is equal to 0, right? Of course. And because it's a reversible process, you can always do that, because for a reversible process, ds is just equal to dq upon the temperature. And of course, like the temperatures of both of these medium, they are the same, right? Okay, That makes sense? Cool. And because dq is 0, du is equal to dw. And that's why du upon dA is equal to dw upon dA. And this is equal to our surface tension, which we'll call it as gamma. Right. So that's all I wanted to say, that gamma can be thought of as both the change in surface energy per unit area change, and also the work done by us per unit area change, right? Because the work done by us is actually equal to the surface energy change, right? So that's it. I'll see you guys in the next video.